Log on, tune in, find out. Another good idea from Cambridge.
Before I start, I'd like to thank John and other organizers for having me here and for such an excellent program. So for the last 2 weeks, I really enjoyed my experience here and attend all these excellent talks here. So really grateful for this opportunity. So today I'd like to talk about give a perspective about the turbulent flows. In particular, I like to focus on the rotating turbulent flows. Well, obviously, it's, as you know, the rotating flows has a lot of different applications. Obviously, there's an application for the program we have here, but it also has some interesting application, particularly like if you go to engineering field, like the turbo machinery, and also in the geophysics problems when you deal with the rotating of the Earth, and also in the astrophysics problems. So there's many different interesting experience, but because I'm here in Cambridge, so I want to mention one of the particular application. So it's a so-called Rayleigh-Taylor instability. So that's is also very important, in particular in the some of the work going on in Lawrence Livermore National Lab. So we have this large laser facility called the National Ignition facility. So try to achieve the nuclear fusion in the laboratory environment. So one of the challenge you have to deal with when you have this kind of laser driven target, very small target, is you want to prevent the so-called Rayleigh-Taylor instability. So Rayleigh-Taylor instability is obviously it's given name after to scientists from the Cambridge University. So basically what the Rayleigh-Taylor driven flow is, you have a heavy high density fluid, then with underneath with a low density fluids with some very small scale perturbation between these two fluids. And if you let them go, then you will start to develop all this kind of instability driven flow. So if you look the picture, you will see like if you have the heavy stuff on the top, the lighter stuff underneath, then you will start to develop all these kind of instability flows in terms of the like the bubbles and the spikes. Depends on whether you're talking about the interpenetration of the heavy and the light fluids. And to make connection to the topic I'm going to talk about here, is this kind of instability also is sensitive to whether the system is subject to rotation or not. So here, if I have basically it's a Rayleigh-Taylor driven flow without any rotatings. So then you basically have developed all these bubble and the spikes. But if you start to apply the rotation with a different speed, then you can see this is a case when you have a not very strong rotation, then you can see there's a small reduction to the growth of the mixing layer. But if you start to apply the rotation with a higher and higher speed, then you can see the development of the mixing layer, Rayleigh-Taylor mixing layer, start to get suppressed. Then you can, to the end, when you have a really strong rotation, then you don't basically suppress the growth of the Rayleigh-Taylor instabilities. So it's just interesting. So basically when you want to study the rotating flows, so one thing important is to know that they have a really important application on all the different aspects of the flows, like what I just mentioned to you in the examples. Basically the rotation, strong rotation can completely suppress the growth of the flows. But one problem is if you look the write down the kinetic energy equation for these kind of flows, these kind of rotation terms, particular term, does not even enter into the kinetic energy equations. So basically, there's a lot of problems in develop models when you want to solve these kind of problems. So what I try to do here is to develop some kind of procedures, basically to study the more fundamental aspect of these kind of flows, and try to use the better understanding of the physics, particularly like the issue like how the energy transfer and with the rotating with this kind of external agency, what kind of the modification you are going to have on the energy spectrum. And once we have a better understanding on this kind of physics, then eventually we want to fold this kind of physical understanding into different models. For example, you want to incorporate this kind of external effect into the subgraph models when you do the large eddy estimation. And also in the case when you want to do the Reynolds average Navier-Stokes equation, this kind of RANS models, you also want to have a way to incorporate this kind of effect based on the physics into these kind of models. And to the end, eventually, I like to have this as a more general process to apply to the different turbulent flows subject to the external agency, such as like stratification and the combination of the rotation and the stratification. All right, so basically, let me just start from something I just mentioned. One of the first things you can have is to examine what kind of modification of this kind of external agency on the spectrum of the turbulent flows. So this first step we want to do is try to consider how this kind of strong rotation modifies the energy spectrum. So this will give you the first indication on how physics has been modified. So for these kind of problems, so basically one of the starting point is we recognize there's a very strong similarity between the MHD turbulence subject to the isotropic turbulence and these kind of flows, such as the rotation and the stratification. So both of these kind of flows, you have, for example, in the MHD turbulence, Bob Kretschmann, what he argued is there's a propagating aphanic turbulence, and what they do is to disrupt the phase relation and decrease the energy transfer between the large and the small flows. And we can easily draw the parallel when you have a strong rotation, is the rotation will cause a plane wave to propagate with a phase speed such as twice omega is the rotation rate, then normalized by the k values. So k is a wave number. So basically, so you can also make this kind of argument for stratified flows and obtain the similar kind of results. So these basically indicate the traditional homograph type of picture for the turbulence is no longer applied when you have a strong external agency. The reason is when you have a strong rotation or the stratification or both, you introduce additional time scale into the problems. So you no longer just simply have the classic nonlinear time scales. Basically, you have an additional time scale which is much shorter, and they play a more dominant role in term of control how the energy can transfer from large scale to the small scales. So if we look at the energy transfer process of these kind of flows, then you can see the time scale for the most important time scale is so-called triple correlations. And this is a time scale that control the rate of the energy transfer from large to small scales. And these basically, in the situation with the external agency, you have to take the time scale which is given by the external time scale in this case, for the rotating flows, is a time scale related to the rotation rate. Okay, so basically, here is a dimension analysis. You can easily write down epsilon here is the energy flux transfer from the large scale to the small scales. So this is given by this kind of triple time scales multiplied by the wave number to the fourth power and the energy spectrum to the second power. So this is some dimensional analysis come out easily, and obviously this time scale, if there's no external time scale, okay, so we just simply plugging back the nonlinear time scale of the chromograph, then you will recover the classical chromograph time, spectrum. But when you have the external time scale given by the rotation rate, then you are going to have a different kind of energy spectrum of the problem. All right, so if we apply this kind of process to this kind of problem, what kind of results we are going to get? Okay, so as I mentioned, if in this case, the most important dominant time scale is given by this, it's a 1 over rotation rate, then you can derive the energy spectrum for these kind of flows is given by the k to the minus 2. So this is in contrary to the classic chromograph of k to the minus 5/3. And not only that, but also the prefactor in front of the energy spectrum also get modified. So it's not only depends on the energy flux as the chromograph does, but also this external effect of the rotation rate also come into play. So there are two effects. Not only so this exponent of the spectrum get modified, but also this external agency come into the play as part of the prefactor of the problem. All right, so how do we know this makes sense? So you can always do the direct numerical simulation of the problems. And so this is one of the calculations we have done previously. So what I plot here is a wave number normalized appropriately, and also plot vertically is so-called compensate energy spectrum. So this is the energy spectrum from the calculation, and it's compensated by multiplication of the k to the second power. So in order to compensate to the energy spectrum like this, k to the minus 2. So basically to have a flat line indicate basically energy spectrum go to the k to the second power, minus 2 power. And as you can see, as the flow eventually evolve, then we go to the almost a constant line. So that indicates energy spectrum will eventually evolve into the k to the minus 2 spectrum. And also there are several experiments were carried out, and here is one of the example published a few years back. Then you can see they have carried out in University of Texas several experiments with the different method with a different Reynolds number, which are quite high. Then you can see here they have the plot of k to the minus 2, and also with a dashed line is k to the minus 5/3. And clearly you can see the k to the minus 2 spectrum is more appropriate for this kind of problem. All right, so here previously I described the very phenomenologic type of approach to get to the k to the minus 2 spectrum for this kind of rotating flows. But here I can just make it more elaborate. So I'm not going to give you too much details, but what I just want to emphasize is to use a statistical approach, the closure theory of the turbulence, such as direct interaction approximations. So these are the second order closure based on the statistic mechanics. You can easily recover these kind of spectrums. So basically what you write down is, you write down the so-called DIA inertial range energy balance equation with all these complicated forms. Then you look for the time time scale of these problems. And in this case, the dominant time scale, as I mentioned, is no longer going to be the Kolmogorov nonlinear time scales. Then you can basically easily, with the ansatz like this, with some kind of indicates the energy spectrum should be scaled as some kind of power law, then you can easily come up, recover the same kind of energy spectrum I described to you a little bit earlier. So there's a different way to derive such a rotating modified energy spectrum for the problem. All right, so basically what's the story here? So what you can have is you can have a competing time scales. So you have the nonlinear time scale of the classic Kolmogorov. Then you can have the external agency like the rotation, or you can have the stratification. So when you have these kind of competing time scales, then you can have a more generalized energy spectrum. Depends on which time scale is dominant, then you can have the corresponding energy spectrum for the problem. So here is just an illustration for you here. So these kind of a triple time scale I described. So these are time scales that dominate, control the energy transfer of the turbulent flows. So you can easily have the rate of these kind of triple time scales is given by the contribution from both the classic nonlinear time scale, and also you have the time scale given by the external agency. Then once you have this kind of more general structure, then you can easily recover the classic Kolmogorov kind of time scales spectrum with a k to the minus 5/3. Also, when you go to another limit of the strong rotation, then you can have the energy spectrum go to the k to the minus 2. So these basically illustrate of the energy spectrum. So you can have the no rotation. So this is the minus 5/3, or if you have a strong rotation, then you can go to the minus 2. So these basically you can see from the direct numeric simulations. And again here, it's a little bit hard to see, but this is again is a compensated energy spectrum. So for the no rotation, so basically you compensate by the Kolmogorov k to the minus 5/3. So you want to see a flat line, so that indicates, of course, the energy spectrum for the flow is given by the classic Kolmogorov kind of spectrum. And for the system with a rotation, what you compensate is a k to the second. So basically here, the flat line indicates the energy spectrum get modified to the k to the minus 2 situation.
Your interpolation formula for
Right.
tau 3 is right.
Yes.
Then doesn't it mean that the transition between spectra happens at a different wave number?
Exactly.
Okay.
Steve, that's an excellent point. Actually, so that's exactly the point I was going to give a little bit later. But that's exactly right. So, but these here is basically just a cartoon to indicate how the slope can be modified. But your point is exactly right. Okay, so actually it's somewhere right here in the next view graph. So you're a little bit ahead of me already. So basically, so what you have is, for the really large scale, so you can have any kind of the, large scale structure, so they can scale like k to the second or k to the fourth power. So like according to Softman or Batch. So you can have all the different large scale kind of the energy spectrum. But like what Steve just pointed out, depends on the time scales. So you can have the minus 2, so you go like this. Then obviously you can have the Kolmogorov energy spectrum go to the minus 5/3, and you recover like this. Now one of the subtleties eventually depends on how strong the rotation is, then whether the dissipation scale right here is going to be affected by the rotation, the external agency or not. All right, so but that's really one of the interesting things is then you are going to have some kind of a break of the kind of spectrums. Then you can estimate the wave number where the separation of this kind of two slope take place. Now going to the application. So one of the important things when you do the modeling, in any of the application is usually you want to have eddy viscosity in your calculation. Basically, you cannot resolve all the small scales. So when you do a large eddy simulation, or even the Reynolds average Navier-Stokes equation, you want to have an eddy viscosity that can take care of the small scale, unresolvable small scales. Now, one of the challenges is how do you build in this kind of the effect of these external agents into the problem. But here, once we have done the analysis and modified the energy spectrum, then we can do analysis and we can easily show if you have a modified k to the minus 2 spectrum, then you can automatically have eddy viscosity that has a rotation dependence. And it gives to the scale as 1 over the omega. So that means if you have a really strong rotation, then eddy viscosity is going to approach to 0. So basically, that's sort of interesting scaling analysis you can easily do. And when you actually look more elaborate, then you can actually to combine the effect of rotation with the conjunction with the mean vorticity. So that's a normal thing to do is you can combine this kind of mean vorticity and the rotation together. So you can incorporate this kind of external effect into your model in a more consistent way. All right, then again, when we have this kind of two competing time scales, so what kind of effect they are going to have? So for when you have a rotation, then you can easily extend what kind of associate time scale of the problems. Then you can basically work out different kind of limiting case. So obviously for this kind of problem, you have a strong limit for the rotation. So you can easily work out what kind of energy spectrum you can have. And for the leading order, so that's the expression we have. Then you have the higher order correction, then you can keep going when you have the asymptotic expansion. But also, you can work out a small, weak rotation limit. So if you have the rotation, but the effect is not dominant, but you still will have the correction to the Kolmogorov kind of the energy spectrum, and with the additional term contribute by the rotation. So then obviously you can construct some kind of maybe like per day kind of forms for the eddy viscosity in terms of like these. So you have the traditional eddy viscosity for the people working on the turbulence modeling and the model for the eddy viscosity. So it looks like this kind of thing. So this capital K here is a kinetic energy of the system. So this should be different from the lowercase k, that's a wave number. So here K is a kinetic energy. Epsilon again is the energy flux of the turbulent flows. Then you can have this kind of formula basically to give you to the eddy viscosity to the correct form in the different limit. The strong rotation, weak rotation, and no rotation. So, all right. So once we talk about all these kind of applications, then we can say, well, for some of the Reynolds average modelings, so you need to have some additional information in order to have the correct input for your models. So then, obviously, you want to study more detailed physics of these kind of problems. So there are more things you can do on top of the energy spectrum you can have. So there are a couple of things we can study. For example, you can do a direct numeric simulation, try to understand this kind of rotating flow a little bit better. So what you do is you apply the forcing as a driver, then put a strong rotation into the system. So what you find is as I indicate before, when you have a strong rotation, basically what you have is basically you shut down, have the phase scramble of the system, basically shut down the energy transfer from the large scale to the small scales. So basically, essentially, as time goes, basically the dissipation of the problems eventually going to decrease because you have less and less turbulence going from the large scale to the small scales. So as time goes, as like going these are time goes here, then the dissipation of the problem starts to decrease because you have less and less energy go to the small scale and get dissipated. And because of this process, and because we already also have in this particular calculation to have a forcing to supply the energy, then you can see the kinetic energy, because it cannot be dissipated. You put more energy into the system by forcing, and they have nowhere to go. So what happens is the kinetic energy will start to accumulate and stay in the large scale of the problem. And you can also look for the other indication of the decrease of the energy transfer between the large and small scale by look the skewness factor. So that's given by George Batchelor. And you can see for the rotation, basically the value decrease. So that indicate a suppress of the energy transfer between the scales. Now, one other thing you can do is to look for these so-called spectrum dynamics of these kind of flows. So what you can do is you can construct the energy transfer equation in terms of the vectors. So this is the energy spectrum, so calculate by the product of the velocity ui and uj, and take the Fourier transform into the energy spectrum tensor. So if you look at the diagonal components, then you can see for the energy transfer term, so this is a double velocity product, and the transfer term is a triple velocity product terms. Then you can see if you don't have a rotation, then without talking about too much detail about here. So one thing you want to notice is energy transfer for the non-rotating case is much bigger than the case when you have the strong rotation. So that's another signal to you. So when you have a strong rotation, then the energy transfer between the scales decreased. And also, another way you can look this kind of analysis is you can look the anisotropy of the problem developed by this kind of external agency. So what happens is you can look the transfer function component is parallel to the direction of omega, and also the transfer function perpendicular to the omega. Then you can see one is much bigger than another one, and also you can see there's some of the indication this kind of function can tell you the direction of the energy transfer. Basically, you have the inverse cascade from the small scale to the large scale. So these are just a different tool. You can have a better feeling on how the physics work in this kind of problem. All right, so let me just quickly talk about how this kind of information you can use for you to build into the models. So as I mentioned, one of the model for when you're dealing with the turbulent flows is to so-called Reynolds average Navier-Stokes models. So these kind of model, basically, if you think about this after the analysis, is they have to satisfy two consistency conditions for these kind of flows. One is basically the cascade is disturbed and suppressed. And another one is, as I indicated, so there's a two-dimensionalization of the problem due to this kind of external effect. So when you go to the develop the model for these kind of flows, so these are the limiting case you want to satisfy. So when you translate this kind of condition into the turbulence models, then you have the dissipation rate of the flows from the large to the small scales. Then this kind of dissipation rate need to go to 0. And also, as I indicated, for the models, the eddy viscosity is dependent on how strong the rotation is, and also need to go to the 0 when you take the limit of omega go to infinity. So one of the issues when we start to do this kind of problem is some of the classic models basically quite widely used in the different applications. They don't satisfy these two conditions. So let me just list two of the very famous models in turbulence models. This Landau Lander and Reeve and Rody model. So this is a very famous model applied in many cases in the turbulence models. When you tag this model to the strong rotation limit, so what you find is the dissipation rate in this model is not affected by the rotations. So basically, the first condition I talked about is not satisfied. And this modified model from this classic model, so developed a little bit later, and in this kind of case, the eddy viscosity is decreased by having the epsilon increase. So obviously, let's go to the other direction, what we talk about. When you have a strong rotation, the eddy viscosity need to go to 0 rather than increase. All right, so there's some kind of a need to be able to have the model can satisfy the two conditions we talked about. So if we go back to the analytic theory based on the two-point closure theory, and from the modified energy spectrum, -2 energy spectrum, and also from the energy flux function I described to you a little bit early, then you can easily derive the energy spectrum which satisfies the condition requirement I discussed. So here is just without going into the details, so let me just mention there's some different method. So this additional procedure by the Chested. So he also as a different way, but with the same kind of information I give, the modified energy spectrum and the suppress of the energy transfer using a different methodology, you can arrive the same kind of conclusion, and you can get the same kind of correct models for this kind of problems. So once you have this kind of model, then you can look at the different limit. For example, in the long time limit, so what you have from the calculation is you need to have the kinetic energy is going to go to the constant, as I mentioned, because energy transfer gets shut down by the strong rotation given by this kind of condition, because there's no energy transfer between large and small scales. Then you can have look the long time limit. So you can solve this kind of decay turbulence problem with the rotation into the system to give you the correct limit for the problem. All right, so before I conclude here, so let me just mention some of the point I allude to a little bit early, is when you have this kind of external effect, then not only you can modify the inertial range energy spectrum. So again, so this energy spectrum we talked about here, and you have when you have the rotation, then you have the -2, then it's possible you can have the recover of the classic homograph spectrum. But obviously, where the breaking point in the matching point of the spectrum in the wave number space depends on how strong the rotation rate is. So basically, it's a rate between the two, how strong the interplay between these two kind of time scale of the problems. And if the rotation rate is really strong, so this kind of effect might extend all the way into the dissipation range. So basically, you can write down the different kind of the ordering of the problems. Basically, if you have the normal ordering, basically this kind of is a case. What I draw here is you have the rotation minus modified energy spectrum that recovered by the chromograph. Then you will have the traditional dissipation spectrum of the turbulent flows. But then you could have the inverted orders, because if this kind of effect is very strong, then the omega will go all the way into the dissipation scales, and you have to have the dissipation energy spectrum that's dependent on the rotation rate. So that's something you have to work out. So I'm not going to talk about that here. So these are given in this analysis here. All right, so let me just conclude here because I don't want to keep you here too long. We have 2 talks today. So let me just quickly summarize the message I have. Is the whole idea is you have this kind of turbulent flows, now you have this external agency. So the idea is to develop a general procedure, not only can apply to this kind of problem, but also to the other kind of application like stratification and combination of the rotation and the stratification, and maybe some other kind of problem, such as MHD turbulence, is to understand the physics of this kind of problem a little bit better, then try to fold them back into the more useful models where people can apply for the different applications. So this basically is the whole idea on this kind of procedure. So specifically, so what I mentioned here, just as a summary is basically we focus on how this kind of strong rotation, so they modify the cascade dynamics, so that not only including the modification of the energy spectrum, but also how the energy is being transferred between the large and the small scales. And these kind of modification of the energy spectrum and the transfer, basically they provide a starting point for the model development. Okay, so in the application where you have this kind of turbulent flows with the external agency, then these might be a recipe we can follow to develop better model to make sure the correct physics can be incorporated into the model. So the model will automatically take into account this kind of different physics. And these basically one of the example is we derive the additive viscosity that depends on rotation rate. You can have a strong limit and a weak rotation limit, and basically it's no rotation limit. And also I mentioned when you have the Reynolds number, Rand's kind of the modelings, that's another kind of model other than the subgram turbulence, large eddy simulation models. When you have these kind of applications, then you have this kind of two limit you have to satisfy. And there are some kind of example I'm not going to mention here. For example, when you apply to some kind of engineering flows based on this kind of approach, give you good results. And as I mentioned, so we want to apply these kind of things to the other kind of problem appropriate for us for this kind of program, such as a stratified flow and combination of the stratified and rotating flows. Thank you.
Thank you. In the atmosphere, we normally, John and Mike will disagree with us, I think, but we resolve in your idealized problem, the k to the minus 2 past the spectrum, because
Right.
often the simulations comes there.
Right.
And in some ways the 3D turbulence is sort of parametrized, although it's not obviously not quite the same. And one of the themes of this program is stochastic backscatter, so the way in which the small scales can propagate energy back up to the large scales. Well, you've computed the energy transfer rate and you show the transition between the downscale energy transfer and backscatter
Right.
up. Can you say something about what scales the energy is projected onto when it's an upscale energy transfer and where it comes from? Can you quantify that in these calculations?
I think you could, yeah, but I just have to, look into, depends on the particular application, but I think you can do this kind of analysis to see where's the starting point, the effect between these two different scales. And
So based on what you've done, is the upscale energy, is it that the energy is being passed through the cascade, or we were talking about this last night, or is it that it's passed immediately up to the very largest?
what is, yeah, I think as far as we see, it's sort of an inverse cascade process, but eventually, obviously, you go to, for the computation, you go to the largest, the scale of the problem. So until the system depends on your computation size, so eventually you will go to the largest scales of the problem.
could you show the Paddy approximation to the eddy viscosity?
Sure.
I was wondering at what sort of level the rotation kicks in the. So it relates the rotation to. Well, that's presumably that's just the scaling of.
Right. So these basically give you, see as I mentioned, the viscosity is a 1 over omega dependence. So this is a.
Because that's C.
Oh, so
So
right.
If you wanted to know in a real problem whether you should have a rotationally dependent eddy viscosity, you want to know a value of C.
Right. No, I think always for these constants, the proper way to do is to calibrate the constant. So when you go to the very strong rotation rate, then basically this term will dominate. Then basically you can calibrate this constant along with the traditional coefficient to see what the proper value is.
So is there some literature that one can refer to now for that?
So I think it's available in the data, but I never, go to evaluate this constant. But obviously, this kind of number is you can pull out from the simulation data, so it's available.
Most atmospheric models, the sort of truncation is at a scale where the observations indicate it should be in the -5/3 range, I think. And whether the models themselves manage to reproduce, that's another matter.
But that's a different to his 5/3, Mike.
So, well, let's just try and.
His 5/3 is a 3D isotropic turbulence 5/3. Whereas the atmospheric one isn't.
It comes from some other reason, but it's still a -5. So how does that relate to what you're saying? Or how do these things relate? So, people think this -5/3 they observe at fairly large scale in the atmosphere. It clearly isn't 3D isotropic turbulence, but one of the theories is stratified turbulence. There's also other things going around. But either way, it is a -5/3 law.
You get a -5/3 from an energy cascade, irrespective of providing you satisfy the Kolmogorov assumptions. An energy cascade gives you 5/3 irrespective of the dynamics.
Yeah, that's right. But all I'm saying is that at the scale where we truncate most of our models, observations say you're in a -5/3 range for whatever reason, and therefore your strategy for model design should be consistent with that. In a sense, the atmosphere isn't really rapidly rotating in the sense turbo machinery is rapidly rotating. I think that might be where the difference is coming from. The time scale is sort of a day, something like a day or a bit less for an atmospheric rotation.
Maybe the weak rotation limit.
That is really weak rotation.
Yeah.
Well,
Perhaps so. It's perhaps not in the middle.
weak compared to what?
Yeah.
Okay. Well, how do you, when you say weak rotation, so what's that weak defined relative to your middle bullet?
Right. Well, basically it's it's Rossby number is a good parameter to think about. So as an organizing parameter to do the perturbation
Look at weather systems. The Rossby number is say 0.1, but as you go down towards the scale which you're truncating your model, then it's of an order 1 or bigger even. Stratification is still very important. The way stratification really takes over.
Yeah.
And rotation still has some effect. You can't ignore it. It really dominates.
That's the difference, and that's sort of the direction. I like to look more.
But the other
sort of
thing is,
interplay.
there's a huge gap between the scale where the Rossby number. If you applied calculate the Rossby number based on the atmospheric viscous scale, it would be huge. I think he had a case where you had Rossby number, which is still small at the viscous scale. A completely different regime because of that, but that will be probably correct for turbo machinery, I guess.
Yeah. So the idea is to have these sort of broad enough so you can have go to the the appropriate limit, either the weak or strong or somewhere between. So that's sort of the idea to try to have a framework so we can build this kind of effect in here.
You said your energy transfer epsilon should decrease as your rotation gets stronger.
That's right. That's right.
Actually, that depends how you set your problem up. So you could imagine forcing in such a way that you fix epsilon. You have a fixed rate of energy input, and so your throughput and dissipation must equal that. I guess my question is, what do you keep constant then, as you vary the rotation rate to?
Well, the energy provided is always, so for this particular application, is always in the very large scale. So you give the energy injection into the large scale, and you want to see, for the traditional S-chapter turbulence, is you recover the Kolmogorov spectrum, with minus 5/3, and see establish the inertial range. So basically, here is you want to see what's going to be changed. So when you apply the external agency into this problem, how do you modify the inertial range? So basically, here you want to have a effect. That's basically scramble the different phase correlation of the inertial range. Then basically the net effect to the end is you basically systematically reduce how effective you can transfer the energy from large scale to the small scales. And to the end, if the rotation is really strong, basically you destroyed more or less the whole triadic interaction type of process going on in the inertial range. And basically you shut down more or less the way to transfer the energy from large to small scales.
Seems to be a link between this, what you're just saying now, and your it's like the mathematical thing. So if you look at the results on convergence of Euler to QG, for instance, that says that if the Rossby number tends to 0, you'll get first order convergence solution. And that can't be, that can only happen if you like, the wave number at the top of the inertial range decreases rapidly the Rossby number, because otherwise you can't possibly converge that fast. So it's really saying that the flow has to change, which is, I think is exactly what you've just been saying. So I just think, have you sort of linked what you're saying to that sort of mathematics at all?
Exactly. Yeah. Perfect. Yeah.
Thank you very much.
Thank you, John. Thanks.